You are currently the only person in this conference.
One of the last questions from one student was about the necessity, the requirement for the rotation of the silicon seed with respect to the crucible. And this is mostly due to the fact that in the pulling up of the silicon ingot, we have typically to add dopant, okay, to pull up doped silicon crystal. What is the reason to introduce dopant to the growing silicon ingot? This is because we want to start from a silicon ingot, and as a consequence, silicon wafers with a well-known fixed dopant concentration. That may be N dopant or P dopant, but it's much better to start with a fixed, well-known, and reproducible dopant concentration than starting from a substrate whose impurities concentration is unknown and unpredictable. Okay. Moreover, consider then in the fabrication of microelectronic devices, okay, you have typically to electrically insulate similar devices that are fabricated on the same substrate. Okay, so they may be both bipolar or CMOS transistor, and such insulation is typically achieved through the reverse biasing of p-n junction. Okay. So, for instance, if the substrate is N-doped, by doping locally the substrate through P-dopant, you can reversely bias the p-n junction of the different devices so as to achieve a global electrical insulation, so no crosstalk between the different devices. Okay? The same is, of course, if you pull up P-doped crystals. Just to show you an example, what I reported in this slide is an excerpt of the datasheet of the silicon wafer provider, okay, in which you see just a list of some characteristics, some features, okay. Besides the thickness, you see that you have the doping type, okay, is a p-type dopant, and specifically boron, that is the unique p-type dopant currently employed in the microelectronic industry. And you see that you have a value related to the resistivity, okay. Resistivity is, of course, inversely proportional to the dopant concentration. Okay, so you see that there is a certain amount of boron that is introduced into the growing crystal, into the growing ingot, so as to obtain a specific dopant concentration, and as a consequence, resistivity. Moreover, you see that the resistivity is not specified as a single value, but is specified according to a certain tolerance, okay? In a few seconds, it will be clear why you cannot guarantee a fixed value, but you can just guarantee a certain range, and as a consequence, a certain tolerance. The reason is basically due that the concentration of the dopant that tends to diffuse into the growing solid crystal is not the same as in the melt, okay? And in particular, dopant tend to remain in the melt than entering into the solid growing crystal, okay? This effect can be physically described and mathematically modelized through a parameter that is the so-called segregation coefficient. That is nothing more than a ratio, okay, so K is the segregation coefficient, is just a ratio between the concentration of dopant in the solid growing crystal versus the concentration of dopant that remain in the melt, okay? Unfortunately, or in any case, this value is less than 1 for the typical dopant for silicon or other semiconductive materials. For instance, you see that in this top table, I introduced the 3 most important dopant for the silicon technology. Okay, so we have already seen boron as the P dopant, while phosphorus and arsenic are the typical N dopant, as we will see better in the future in the dedicated doping lecture. Okay, so you can appreciate how for both the P and N-type dopant, the segregation factor is less than 1. Now, while in the case of boron, the situation is not as much critical because it's less than 1, but very close to 1. Okay, for the case of both phosphorus and arsenic, this value is significantly lower than 1. Okay, what is the effect? The effect is that during doping, okay, during the pooling of the silicon ingot, okay, you have a concentration of dopant that become increasingly higher while you pull up the ingot, okay? So basically, okay, I count on the webcam that also the student at home can see. If this is your silicon ingot, okay, while you pull up the silicon ingot from the melt, okay, since the dopant prefer remaining statistically in the melt, okay, you pull up silicon ingot with a progressively increasing dopant concentration, okay? So at the end, a silicon ingot will not have a uniform concentration along the height, okay, but a concentration that will be characterized by a significant gradient that will be proportional to the value of the segregation factor, okay? In particular, the top part of the silicon ingot will be characterized by a lower dopant concentration, while the bottom will be characterized by a higher dopant concentration, okay? Any questions so far? Okay, while I am in the room, when everything is working, I have the opportunity to see in parallel the chat and the students. So when everything is working, just half an hour. Okay, how can we do a uniform concentration doping? There is no way with this technique, there is no way with the alternative technique that we will describe in a few seconds, that is say the floating zone. There is no way, there is no solution. And this is the reason why, at the end, you have a tolerance in the determination of the resistivity, that is a consequence of the determination of the silicon dopant. And this is why, at the end, the ingot, besides being reduced to slices, what we will call the wafers, moreover, these wafers are separated into lots. Okay, so you will have a first lot, a second lot, a third lot, and so on. Okay, each lot is characterized by a specific range of dopant concentration inside a certain tolerance, and as a consequence, a specific resistivity range. Okay, of course, the narrower is the resistivity range you want to provide your customer, the smaller will be the lot that you can exploit to commercialize that specific dopant concentration and that specific resistivity. Okay? Okay, yes sir is asking that he doesn't understand why there is a gradient of concentration between the top and the bottom. Okay, the point is this one, okay? The dopant that you load into the melt, okay, prefer remaining in the melt, okay? If the segregation coefficient is 0.3, it means that there are 3 dopants that enter into the melt and 10 dopants that remain that enter into the solid, 10 dopants that remain to the melt, okay? So the effect is that while you pull up the ingot, of course, you consume the melt, you consume the material, you reduce the liquid silicon that remain in the crucible, but the dopant concentration will increase, okay? So while pulling up, you pull ingots that are more and more doped. Is okay? Any further question? Okay, it seems not. Perfect. There is a second issue related to the Czochralski technology, okay? The second issue is connected to the potential oxygen doping, okay? Why? Because the oxygen is present in the crucible. If you remember, the crucible is made of quartz, okay? Quartz is basically silicon oxide, and as a consequence, since there is a physical contact between the quartz crucible sidewalls and the silicon melt, there is the possibility that some oxygen not properly bound to the silicon oxide molecule may enter into the melt and as a consequence contaminate the growing silicon ingot, okay? So to prevent or to limit the problem due to the oxygen contamination that we will see in a few seconds, there is an alternative approach, an alternative technology for the transformation of electronic grade polycrystalline silicon into monocrystalline one. This is why there is an alternative pathway to the Czochralski process. that, if you remember, I anticipated in the last lecture, that is the so-called floating zone method. Okay? So in the following, we will see what is this floating zone process method. It is an alternative method, an alternative technology with respect to the Czochralski one for the transformation of the electronic grade polycrystalline silicon, that, if you remember, is the output of the Siemens process, into a monocrystalline electronic grade silicon ingot. Yes, tell me.
But why does it change with respect to?
Because each dopant has different characteristics, different physics. If you give a look, boron belongs to the third column of the Mendeleev table, phosphorus and arsenic to the fifth one. Okay, and indeed, if you give a look, phosphorus is a little bit smaller than arsenic. Okay, so they are different atoms. But if you consider the segregation factor of phosphorus and arsenic is very, very similar. But yeah, totally change of the reactivity, the diffusivity, and the physical properties. Sorry?
You said K changes with that, and this will increase, of course.
Yeah. Okay. Okay. So, floating zone process. Okay, remember, is an alternative approach to the Czochralski method for pooling and obtaining monocrystalline electronic grade silicon ingot. Before explaining how it works, okay, I would like to highlight which are the troubles, the problem related to the oxygen contamination. Okay, first of all, oxygen is a dopant for silicon. Okay, it may be a thermal donor in silicon. Second point, it may locally alter the mechanical properties, okay, and in particular the mechanical strength. But what is, without any doubt, from a microelectronic point of view, the most critical issue is that oxygen may favor the local precipitation of impurity. So it works like a sort of gathering site, a trapping site that attracts and favor reactions with respect to other unwanted contaminants. Okay? And that's the reason why, not for all the application actually, but for some microelectronic applications that I will show you are basically the high power, high temperature, high voltage electronic application, it's extremely important to minimize the oxygen concentration. And so to choose as an alternative method with respect to the Czochralski, the floating zone one, okay? Well, how does the floating zone process works? We start from the polycrystalline electronic grade silicon ingot that, if you remember, is the output of the Siemens process, okay? With respect to the Czochralski method, there is no melt in this case, or better, not real melt. The polycrystalline silicon ingot is mounted upside down, as shown in this drawing, okay, with a rod holder on the top, okay, and a seed on the bottom, okay? The seed is always necessary. Without the seed, there is no reference, no solid state monocrystalline reference to obtain any kind of order, any kind of crystalline order, any kind of monocrystalline growth, okay? So the seed is placed, in this case, in the bottom part, okay? With respect to the Czochralski process, in which we have a melt, in this case, the energy is provided through an external RF coil, okay? The one depicted here in this drawing, and here in the real picture showing a real floating zone process. The role of this RF coil is to locally provide sufficient energy. Just to be clear, sufficient energy means that you locally heat up silicon, polycrystalline silicon, slightly below the melting point. Slightly below the melting point, okay? Just under the fusion point of silicon, okay? This kind of temperature is sufficient to guarantee the plastic deformation of silicon and largely sufficient to guarantee a wide diffusion of silicon atoms. Okay, so silicon atoms, when subjected to a similar energy provision, okay, they can move, they can diffuse, and when they cool down, they tend to rearrange by following the crystallographic orientation, the crystallographic order provided by the seed. Okay? In particular, in this animated GIF, you see how the system works. Okay, so the RF coil will move from the bottom to the top very, very slowly, providing a local heating of the polycrystalline silicon ingot, and so favoring the diffusion of the silicon atoms from the polycrystalline sites, polycrystalline structure, to the monocrystalline one. Which monocrystalline structure? The monocrystalline structure that will be provided to the silicon ingot is the one that is determined and fixed by the seed. Okay, so it's the seed that will guarantee and will generate the correct crystallographic orientation. Without the seed, there is no hope. You can heat up the polycrystalline ingot how many times you want, okay? But the atoms, when cooling down, will not rearrange to any crystallographic order, okay? So it's fundamental, a couple of elements: the energy, temperature, high temperature, and the presence of a proper reference, that is the seed, okay? While the RF coil moves up along the ingot, okay, the bottom part of the ingot is transformed into a monocrystalline one, while the top one, still to be modified, is still polycrystalline, okay? Usually, one move, one pass is not sufficient, okay? So this is a process that typically requires multiple passes. The higher is the number of passes, the better will be the quality of the final result in terms of monocrystalline property of the silicon ingot, okay? Any questions so far? Is it clear? How does it work? Okay. Then, you may ask, if this process helps to obtain monocrystalline silicon ingot that are, moreover, not contaminated by oxygen. Actually, this sentence is not totally true. The contamination with oxygen is still present, but is orders of magnitude lower because there is no physical source of oxygen. Okay? There is no physical contact between a crucible made of quartz and the silicon ingot. Okay? So, if this process may ensure a silicon ingot that is both monocrystalline and nearly oxygen-free, why not making all the silicon wafers through the floating zone, okay? So what are the limitations of the floating zone with respect to the Czochralski? Why the floating zone is just an alternative method, and just to be clear, is an alternative method that is used very seldom, okay? The current microelectronic market is covered just for the 2% by floating zone wafers. The 98% is covered by Czochralski. What are the limitations? The first limitation is the cost. Okay? The floating zone tool is a more complex, more expensive, more critical to be controlled, okay, apparatus, equipment. The second point that is highlighted in the previous slide is the limitation in the ingot diameter. Okay? The maximum currently available on the market ingot diameter that may be obtained through the floating zone method is 8 inches. Okay? If you remember, 1 inch, 2.54 centimeter, 8 inches means 20 centimeter. Okay? Okay, so this is the maximum width, the maximum diameter of a silicon wafer obtaining through the floating zone. Okay? The current state of the art for silicon wafers is much bigger. Okay, I will show you what is exactly at the end of this lecture. Okay, so this is an important limitation. Okay, the diameter of the wafer is a key strategic factor for the improvement of the microelectronic industry. Okay, because of course the wider is the wafer, the larger is the wafer, the larger is the number of devices you can fabricate on a single substrate, and so the lower is the manufacturing cost for each single chip, each single device that is obtained. Okay, so of course at the end usually the price is not lower, it's just lower the manufacturing cost, but that's another story. Okay. Okay, so this is the reason, the most important reason why the floating zone process is so limited. As we said a few minutes ago, the most important application for floating zone, that is to say oxygen-free or nearly oxygen-free wafers, is in the fabrication of high power or high voltage microelectronic devices, integrated circuits. Okay, this is because you should know that whenever you have quasi-intrinsically doped regions, okay, this characteristic will allow for higher voltage strength. And in particular, if you have a junction in which one of the two sides is nearly intrinsic, so nearly no doped, you will obtain the maximum breakdown voltage. And the breakdown voltage, the large breakdown voltage, is one of the most important figures of merit for power electronics. Okay? So the floating zone currently find the most important application for the fabrication of high voltage and high power electronics. Nonetheless, the floating zone may be sometimes also involved and exploited for the purification of Czochralski ingot. Okay? So starting from an ingot obtained through the Czochralski, sometimes you may require to purify the Czochralski ingot by applying a further step that is the floating zone. The fact is that, of course, since in the Czochralski ingot you have oxygen, okay, the oxygen cannot be removed. The only effect of this upward RF coil pass is to accumulate progressively the oxygen in the top side of the silicon ingot. Top side of the silicon ingot that at the end will be cut away and not exploited for the slicing and the fabrication of wafers. Okay? Any questions so far? Seems not. Okay, here I had just this morning a slide with some real data just to show you what is the difference in terms of price between floating zone and Czochralski wafers. Okay, so this is an excerpt of the database of a worldwide provider of wafer world, one of the many, not so many, one of the few available wafers provider. Okay, I just extracted some values from the database to show you that considering the same silicon diameter, okay, so 50.8 millimeters, that is to say they are 2 inches wafers. Just to be clear, these are 2 inches wafers. Okay, so very, very small and relatively uncommon with the current technology. Okay, but they were just the first retrieved. Okay, so comparing 2 inches wafers obtained through the floating zone and 2 inches wafers obtained through the Czochralski method, you can here compare what is the difference of price. Okay, there is a 3 to 4 times increase of price for the same kind of wafer. Okay, and this is, of course, a relevant justification why just the 2% of the market is covered by the floating zone. Okay. Okay. I will just stop a few seconds. There are any questions related to the Czochralski, the floating zone, the comparison between them?
With the Czochralski process and the float zone.
Mm-hmm.
So the price difference is
Yes.
4 and 5.
Yes, absolutely, absolutely. Whatever step you had will increase the price. I will show you another example just this morning dealing with the wafer preparation. Whatever is the step you had, it will increase significantly the final price, okay? How do they choose? Yes, sir, is asking, how do they choose the crystal orientation 100, and why do we choose 100 instead of 110, for example? Okay, yes, sir, may I ask you in 1 hour, 1 and a half, when we will speak about crystallography, showing what are the differences between 100 orientation, 110 orientation, and why they may be used both in microelectronics and microsystem technology? Of course, the answer is yes, but. Okay, so I will answer in 1 hour, 1 and a half, hopefully. Anything else? Okay, so the next couple of slides are dedicated just few minutes to show you what are the differences in the ingot formation for a different semiconductor material. Okay, so far we discussed the case of silicon. What about the case of 3,5 compounds? Okay, for instance, gallium arsenide, that without any doubt is the most important 3,5 compound semiconductor material employed mainly for high frequency or radio frequency electronic application. For the case of gallium arsenide, just for example, the manufacturing of the ingot is implemented through a modification of a Czochralski technique, or a Czochralski approach. Why modification, and which kind of modification? The modification is due to the fact that with respect to silicon, gallium arsenide, first of all, is a compound. Okay, so it's not a monoatomic material, but is a biatomic, two chemical species. Two chemical species that, to obtain the correct composition, the correct stoichiometric ratio, should respect some thermodynamic conditions that are not typically easy to fulfill. In particular, in the case of gallium arsenide has a relatively boiling point. This is an issue because, first of all, the evaporation of the material could result in toxic byproducts, and so critical safety issue may arise during the handling and the manufacturing of these materials. Okay, the case of gallium arsenide is much, much more critical than the silicon case and the silicon technology, generally speaking. But what is more important is that gallium and arsenic have dramatically, orders of magnitude, different vapor pressures. That means that whatever process is attempting to mix gallium and arsenic by providing them thermal energy, so heating them, okay, will generate extremely different vapor pressure of gallium arsenide and arsenic that, as a consequence, will not mix in the correct mixing ratio, in the correct stoichiometric ratio, that of course is 1:1. Okay, so to prevent this issue and to guarantee the formation of the correct compound with a 1:1 stoichiometric ratio, you need to modify the Czochralski process by applying some technical tricks, which are the most important. The first one is that the chamber is pressurized. I will use this drawing because it's a little bit bigger, okay? Sorry. The Czochralski reactor is pressurized. You see that you work at a large, very large pressure, 200 atmosphere. And moreover, is pressurized with a mixture of argon, neutral gas, and another gas that is containing arsenic. Why arsenic? Okay, this gas is in particular is called arsine. Why arsenic? Because if you compare gallium and arsenic, it's just arsenic, the one with the much larger vapor pressure. Okay, so by pressurizing the chamber with a large concentration of an atmosphere containing also arsenic, you reduce the risk of arsenic evaporation. You minimize the risk of arsenic evaporation. But this is not sufficient, okay, because the kind of safety about the limited arsenic evaporation will be just statistic. So to have a physical barrier against the arsenic evaporation, you place on the top of the crucible a boron oxide layer. Okay, so with respect to the crucible that was employed in the Czochralski method, that was an open surface, a free surface crucible in which you just put silicon with no cap on the top. Okay, in this case, you use a cap that is made of boron oxide. Why boron oxide? First of all, because boron oxide doesn't react with gallium arsenide. Okay, so is an inert material producing no byproduct with respect to both gallium arsenic and the gallium arsenide compound. The second is because in the modified Czochralski process, the top boron oxide layer will melt at a lower temperature, 500 degrees, with respect to the temperature at which you have the start of the reaction between gallium and arsenic. Okay? So the aim of this boron oxide is to behave like a sort of melt encapsulation layer that will seal, that will close the top of the crucible, suppressing any evaporation. Okay? All the other details are absolutely similar to the Czochralski process. I mean, we need a fragment of a gallium arsenide seed, a monocrystalline gallium arsenide seed, to be dipped through the top boron oxide layer into the gallium arsenide melt. Okay, the melting point for gallium arsenide is slightly above 1,200 degrees. And then through a puller, you have to pull up the seed, and depending on the pulling speed, you will pull up gallium arsenide ingot with a certain specific diameter. You remember that the faster is the pulling speed, the smaller will result the ingot diameter. Okay? So you see that is similar as in terms of layout and structure to a Czochralski process, and indeed it is called a modified Czochralski process, and in particular liquid encapsulated Czochralski. The liquid encapsulation is due to this boron oxide layer. Of course, just as to anticipate one of the possible questions, the ingot will be covered by a sort of a crust made of boron oxide that at the end of the process, I will show you, must be removed, but there is a dedicated process that we'll also analyze for the case of the silicon technology that provide a sort of outer surface abrasion of the ingot, and that automatically, as a consequence, will remove this boron oxide layer that will remain adhered on the outer surface of the ingot. Okay? Any question? I didn't understand the role of boron nitride. Okay, the role of boron nitride, I didn't cite the role of boron nitride. Boron nitride in this case is the crucible, the material of the crucible. Okay, as you can see, is no more quartz, but is boron nitride. Why boron nitride and not quartz? Because as we are seeing today, and as we will see a lot of times in this course, whenever you host a material into another, simply, whenever you put some materials, semiconductive, metals, or any other one, into another, into a crucible, into a reservoir, into a liner, in the evaporation, and you perform a temperature, high temperature activated operation, okay, you always have to prevent any unwanted reactions between the reservoir and the material that is also inside. So, for the case of gallium arsenide, boron nitride is the optimal choice because it's sufficiently robust to withstand the high temperature condition and moreover inert with respect to the gallium arsenide. Okay? Quartz would not be okay because of the reaction between silicon, that is a dopant for gallium arsenide, and oxygen that would favor the oxidation of gallium arsenide. Okay, so hope to have answered to Janina. Yes?
Can you use adapt to the original the name CZ, the process of oxygen from getting?
In the case of the standard Czochralski process, no, because in the case of the Czochralski process, the oxygen is in the crucible, and the crucible is in contact with the melt, and the melt will so it's not a problem of separation or barrier or interface between the melt and the atmosphere and the reactor. It's just a problem that is the quartz itself that is a certain source of oxygen and oxygen contamination. Okay, of course, you do not have to imagine that, okay, thousands and thousands of oxygen atoms are free into the melt, but there is some risk. And in fact, statistically, the Czochralski wafers have, in particular, 2 orders of magnitude higher concentration of oxygen contamination than the floating zone. Okay, so as I told you, with the floating zone doesn't eliminate oxygen, but simply reduce the oxygen contamination of typically 2 orders of magnitude. Okay? Okay, yes, sir, is right. He's asking to repeat the question that was getting class. One of your colleagues was asking if the approach with the encapsulating layer may be exploited also in the Czochralski process to minimize the oxygen contamination. Anything else? Okay. Okay, so at this point, we are dealing with, so let's return to the case study related to the silicon technology, okay? So we have a silicon ingot and hyper pure monocrystalline silicon ingot. So far, we fully satisfied the 3 requirements we highlighted at the beginning of this lecture last time, okay? The next point is how to transform this silicon ingot into silicon wafers, okay? You will see that there are a lot of operations to be performed, okay? So the story is very, very long, okay? First of all, the ingot is subjected to a so-called cropping operation, okay? That is to say, both the top shoulder and the bottom hand cone are cut away and removed. Both of them, okay, here there is a nice picture of one of them, may be eventually reused in another Czochralski process, okay, if, of course, the contamination conditions are sufficiently okay for the new Czochralski process. But they are eliminated, basically, because, of course, they are not provided with the right diameter, that is the correct nominal one for the fabrication of silicon wafers, okay? Now, I tried just an experiment. I know that everything will get totally wrong or not, okay? I see that, okay, it works. You see here on the whiteboard 3 different silicon wafers, okay? A 2 inches silicon wafer, a 4 inches silicon wafer, a 6 inches silicon wafers, okay? So 5, 10, and 15 centimeters. Okay, the diameter of this wafer is exact, is correct, is very, very precise. Okay, and it must be this way. It must be so precise because this is fundamental. Since in high throughput and large volume fabrication facilities, these wafers are not transported manually by operators, but they are transported automatically by robots, okay? And the grasping tool with the robots is, of course, tailored to grasp and to catch objects with a specified diameter, okay? So for the automatic handling and automatic manipulation, this wafer is fundamental that the diameter is exactly the correct one, not 1 millimeter more, not 1 millimeter less. Okay, That's very, very critical. Okay. The second so both the shoulder and the end count, of course, are not provided with the correct diameter. So they must be cut away and trashed or crashed to be reused in another Cherkassky process. The next step is the so-called ingot inspection. Okay, so you perform a triple check on the properties of the silicon ingot: geometrical, electrical, structural. The geometrical check is a check about the potential undersize. Okay, so you check if the silicon ingot is smaller than the nominal diameter. A smaller diameter is a drama. The silicon ingot has to be trashed away. It is no more good. If the silicon ingot is slightly oversized, it can be compensated. And as I will show you, it will be compensated. Okay? So the issues are only if it is undersized. If that, you need to restart. The second check is an electrical check. Okay? So in the electrical check, you have to control for the resistivity. You have to check the resistivity. This is more or less the cylinder, okay, that you obtain after the cropping. Okay? You have to check on the top and the bottom surface of the remaining cylinder the resistivity by performing a 4-probe electrical measurement. Okay? The 4-probe electrical measurement will provide an evaluation of the top and bottom surfaces resistivities. Why? What do you think is the aim of this electrical check? For the dopants. Because if you remember, during the pooling of the crystal, you do not have a constant incorporation of dopants, but you have a gradient that will determine a lower concentration on the top and a higher concentration on the bottom. So you have to check if the nominal expected gradient of concentration is respected. Okay? The last check is a structural check. It's a check about the crystallographic orientation of the ingot. Because, of course, you remember that during the pooling of the crystal, okay, the monocrystalline character and the specific monocrystalline orientation is provided by the seed. So you have to check along the entire length of the ingot. That is impossible. Again, just on the top surface and on the bottom. You have to check if the monocrystalline building is the correct one, with the correct crystallographic orientation. Crystallographic orientation that, as suggested by Yasser a few minutes ago, is labeled with 3 digits. Okay, we spoke about 100 orientation, 110 orientation, 111 orientation, and so on. This will be the topic of the next lecture. Okay, so I hope in 1 hour everything will be mostly clear. Okay? Is okay so far? If we have a gradient of concentration, do not the dopants want to migrate to the lowest concentration zone? Yes, sir is asking that if we have a gradient of concentration, if the dopants do not migrate to the lower concentration zone. Yes, this is correct, but this is, as you know, the diffusion, because here we're speaking about diffusion, is favored by temperature. Okay, so you may have a good diffusion only if you apply a large temperature. Of course, there is no diffusion, or pretty no diffusion, when the silicon ingot is solidified and cold. Okay. While pooling the Cherkassky ingot, you may have, I think, a significant dopant diffusion, but the speed at which you have such diffusion is not sufficient to make the dopant concentration uniform along the length of the ingot. Okay, you will have a minimal, you will gain a minimal sensitivity about how much fast is the solid state diffusion in silicon just after the doping by diffusion lecture that we will have, I think, in 2-3 weeks. Okay, the point is that diffusion will occur, but it will not be sufficient to homogenize, to make uniform the dopant diffusion along the length of the silicon ingot. Okay. The next operation is the so-called ingot shaping. Okay, this is because if you remember from last time lecture, a silicon ingot as the output of a Czochralski process is not a perfect geometrical cylinder. Okay, so it's a cylinder with a sort of waveness, okay, along the outer lateral surface. This lateral waveness is, of course, a problem, because if you do not rectify the outer surface, you will slice silicon wafers with different diameters, and this is not acceptable, okay? So you have to shape the irregular ingots into a pretty perfect geometrical one, okay? This is a quite straightforward and relatively trivial operation. It is performed through a mechanical abrasion. So it is an outer diameter grinding. Okay, it's simple, an abrasion of the ingot outer surface so as to minimize the waveness. Okay. Next operation is the so-called flat grinding. Okay, what are flats? Let's try to reuse the powerful tool of Polytechnic of Turin. Don't smile, please. Here you see that. Let's have a look to this one. Okay, I don't know if the camera is too far or not. Maybe sufficient. Okay, you see that this 6 inches wafer is not a perfect circle. Okay, but it is a circle with a flat region here. Okay, this is in particular a silicon wafer with just one primary flat, one main flat. But if I'm not wrong, yes, this one. If you give a look to this one, it is a little bit hard. It is a little bit harder to see. Okay, but this is a 4 inches wafer. You see here, this is the primary flat. There is a smaller one, smaller. It is a secondary flat, 90 degrees apart. Okay? So you may have a primary and a secondary flat, okay, cut along the entire length of the silicon ingot. What are these flats introduced for? Okay, what is the reason to introduce this flat? Well, there are a couple of reasons. The first, let me say, is not so much relevant. The second is fundamental. Let's start from the former. First of all, the presence of a primary and eventually secondary flat and the angle between the primary and secondary flat, okay, that may be 45 degrees, 180 degrees apart, or 90 degrees as the wafer I just have shown to you a few seconds ago. The presence and the angle between primary and secondary flat is an immediate information about the crystallographic orientation of the corresponding silicon wafer and the type of dopant. Okay, so if you give a look to this sketch, okay, the 4 inches wafer that I've shown you a few minutes ago, is a 100 oriented p-doped silicon wafer. Okay, because it has both a primary and a secondary flat that are 90 degrees apart. Okay? Nonetheless, according to my experience, this is not universally respected. So don't trust on this classification because not all the provider will respect it. Okay? Some providers will have a different labeling, a different nomenclature, different characteristics for wafers with 1 or 2 flats. So it's much more important, the second reason that I still have to explain. The point is that you need at least 1 flat, the primary one. The primary one is always present. The motivation to have a primary flat is that you have a mechanical reference for the orientation of the wafer. Okay? In most of the processes, and in particular in lithography, that is the kind of processes that in technology are used to transfer your device idea to the substrate, okay? You cannot randomly place the wafers in the equipment. The wafers must be properly aligned, for instance, with respect to the crystallographic axis, with respect to the crystallographic orientation. Okay? So the simplest way to provide a reference for alignment is to introduce here a flat. Okay? The flat will provide a reference that will impede any random orientation. Okay? A reference to avoid any random orientation of the wafer. That's the only reason. The larger is the flat, and that's why the primary flat is always present. The simpler will be for the automatic handling to find the correct orientation of the wafer. Okay? Is it clear? Okay. Any question? Okay. Just a few minutes, okay? Then we may have a break time, but consider that we started half an hour later. Okay? Okay. The following operation is finally the ingot sewing. That is to say, the transformation of the ingot into slices that are pretty close to the final wafers. Okay? This operation is performed with a diamond saw. Okay? The diamond saw may be of 2 different types. Okay? We may have a so-called inner diameter saw, like the one depicted here in this picture, in which the inner diameter blade is covered with diamond powder. Okay? Silicon, from a mechanical point of view, is a relatively hard material. Okay? It has an hardness that is close to 8. So that means that you need harder material than silicon to slice and to sew silicon. Okay? This is one possible option. Currently, the most quoted, the most common option, in particular in large volume, large fabrication volume, is the wire, the wire saw. In the wire saw, as you can see, there is an array of metallic wires, okay, visible here in this drawing, partially visible here in this picture. Metallic wires that cut apart the silicon ingot into slices thanks to the cooperation of an abrasive suspension that is periodically provided to the wires. Abrasive suspension that also in this case is mostly composed by artificial diamond powder. Okay? So in both cases, maybe the diamond powder covering the metallic blade or the diamond powder abrasive suspension delivered to the wires is thanks to the comparison between the hardness of diamond and silicon that you can slice the silicon ingot into wafers. Okay? What is the thickness of these wafers? The thickness is usually quite proportional to the silicon wafer diameter. Okay? I mean, just for mechanical reason, mechanical robustness, the larger is the silicon wafer, typically the thicker will be the slice. The thicker will be the wafer. Okay? The typical thickness range is between 300 micrometers and 1 millimeter. Nonetheless, you may retrieve from the market silicon wafers that are even outside this range. Okay, so thinner than 300 microns, or more rarely, thicker than 1 millimeter. Okay? The thickness, well, the thickness mostly depends on the diameter, as I already said, but depends also on the application. I mean, there are some applications, as I will show you in the second part of this lecture, when we will speak about the technologies for the fabrication of MEMS devices, in which you etch and you remove the bulk, so the thickness of the wafers from the backside. Okay, so you etch, you dig in to the wafer from the backside to obtain, for instance, a suspended membrane. Okay, in that case, for instance, it's particularly relevant and strategic to have relatively thin wafers. Okay, and that's the reason why sometimes you may require or ask for silicon wafers that are thinner than 300 microns. Okay, for instance. Another application is in power electronics. Okay, in power electronics, the bulk of the wafer is merely a mechanical support, but is also a dissipation path for the heat that is generated because of the Joule effect into the power electronic devices. Okay, so to improve the thermal dissipation at the end of the process flow for the fabrication of power devices, very often you reduce the thickness of the wafers. Because, of course, the thinner is the wafer, the thinner is the substrate, the faster and more efficient will be the thermal dissipation from the high-power electronic devices to the backside of the wafer, and from the backside of the wafer to the package. Okay? So, variable thicknesses. Any question? Okay. Next operation is still a little bit long, okay, is the so-called edge grinding, okay? What is meant by edge grinding? Well, this is a finished wafer, and unfortunately, due to the COVID-19 disease, I cannot make this wafer circulating along the classes I'm used to make in the previous academic years, okay? But, so, just trust me. Before being a finished wafer, this is just a silicon slice. A silicon slice with the external edge that is very, very sharp. Okay, very sharp. It is a perfect rectangular size. Very, very sharp. Now, the sharpness of this edge is not a problem for the operators that may handle the wafers, okay? Because you will learn that we have always to wear proper protective gloves. And the main problem is that this sharp edge is extremely critical for, again, the automatic handling of wafers, because if the edge is so sharp, it will be statistically very easy to generate mechanical breaking of the wafer in correspondence of these sharp edges. Okay? So to improve, to facilitate the automatic handling, the grasping of the silicon wafers, this sharp edge must be rounded. And as a consequence, you have to perform the so-called edge grinding operation. That, again, simply through a mechanical operation, mechanical abrasion, will transform these sharp edges into smoother one. At the end, if you touch the periphery of the wafer, it is rounded, not dangerous, and not risky for the automatic handling. Okay? Okay. The next operation is the so-called wafer lapping. Okay, what is the wafer lapping used for? let's do, okay, in this way. The problem with the slicing of silicon wafers is that giving a look to them according to the section, okay, they will be rarely a perfect rectangle, and moreover, they may be characterized by different thicknesses, okay? So also the slicing process will be characterized by certain tolerance. The effect is that such slices may have different thicknesses, okay? Different thicknesses, if you want to commercialize the same product with the same characteristics, are of course to be limited, okay? So you have to remove the excess of thickness. Second problem is that after slicing the ingot, okay, very often the resulting wafer is this way. This is, of course, a magnified, a dramatic version of the defect, okay? This defect is called tapering, and the wafer will be tapered. Or eventually, it may be bowed. Okay? Again, not so much. Okay? We are speaking about a moderate tapering and a moderate bowing. But both these situations, of course, are not good for the manufacturing, because what you want to obtain at the end is a perfectly planar slice, perfectly rectified, with both the front and back side that are perfectly parallel, where perfectly means with a micrometric resolution, with a micrometric tolerance, okay? So this means that both for the tapering and for the bowing, you have to eliminate some silicon. This part of silicon are in excess, and they must be eliminated, okay? Eliminated through a proper, again, mechanical, mostly abrasion process. This process is called lapping. Aim of lapping is to reduce any differences in the silicon slices, both in terms of thickness and in terms of section shape. Okay? Now, as already said, to obtain this result, okay, what you perform and what is depicted partially in this picture, you load one or several wafers in these large machines that basically, through an abrasive slurry, okay, and a counter rotation between an abrasive tool and the silicon wafer, produce a localized abrasion that will eliminate the excess of silicon, reducing the significant differences in thickness and section shape. Okay? The effect, the final result, will be a surface like this one, okay, that is mechanically flat, okay? I tried to exploit the reflected light to show you, okay? This is a flat surface, mechanically flat, okay, with a roughness of the order of some microns, okay? Typically a couple of microns is the typical roughness of this surface. And is very good because it's planar. Okay, so at the end, your wafer will rely on a flat surface with the two sides that will be perfectly parallel and perfectly rectified. Okay? Nonetheless, if you give a look to this wafer, you see that while this side is just mechanically flat, where mechanically flat means a couple of microns of roughness, The other side, yes, is optically flat. So you see that it works like a mirror. Is a mirror-like finisher, mirror-like finishing, is optically flat with a roughness that is of the order of a few nanometers, okay? So micrometers on the back side, nanometers, we're speaking about roughness, on the top side, okay? How can we obtain this mirror finishing on the top side, and why we need this mirror finishing? The mirror finishing is performed and obtained through a further technological step that is very similar to the lapping, a little bit more delicate, that is called polishing. Polishing is, again, an operation between a tool and the substrate, counter-rotated each other with the cooperation of abrasive slurry, but with respect to the simpler previous lapping that was basically purely mechanical abrasion. In the case of polishing, is a combination of mechanical abrasion with a smaller diameter slurry and chemical etching. So it's a chemomechanical operation, chemomechanical polishing. It's a combination of mechanical abrasion and chemical etching. Of course, you need to select a chemical etchant that must be selective with respect to the material to be removed. This is to say, in this case, silicon. Okay? So, by using a proper abrasive slurry, typically smaller in terms of average diameter than in the lapping, and by using proper reagents that perform a chemical action, a chemical etching, you transform a mechanically flat surface with a roughness of the order of microns into an optically flat surface with a roughness of the order of nanometers. Okay? What is the aim? Here you see a comparison between the optical reflectivity of a mechanically flat and an optically flat surface. Okay? In a mechanically flat surface, when a radiation, when light is reflected from the surface, the reflection is random scattering. When you have to deal with an optically flat surface, the reflection is coherent. Okay? You have the same angle for all the impinging radiation beam. In these cases, the radiation arrives from an oblique direction. Okay? In technology, we are interested to the case in which the radiation is impinging from the top, because a top striking radiation on the surface of the silicon wafer is exactly what we do during lithography, during the so-called lithographic process. I'm sorry, but all these explanations are full of links, forward links to topics that we didn't explain yet, okay? But everything will be more clear at the end. What is important today is that lithography is the process by which we transfer the layout of your device from your idea to the wafer, okay? To perform a lithographic process, you use objects like this. These are the so-called lithographic masks. It works like a sort of optical filter. It is a slab made of glass covered with a nanometric layer of chromium, removed in correspondence of the regions that should be transparent with respect to the striking radiation. That is to say, this one, okay? So this is a mask that in fabrication is applied on the wafer. so as to leave the radiation pass through the transparent windows. Okay? Now, if the substrate is mechanically rough, or if you prefer mechanically flat, but not optically, the striking radiation will be reflected randomly. This effect will transfer the width of the small feature you want to fabricate, the channel of an MOS transistor, the gate of an MOS transistor, the source and drain of an MOS transistor, few microns, few nanometers. It will transfer this small feature optically into a much wider feature. So the random scattering, the random reflection of the vertically impinging radiation will dramatically affect the resolution of the lithographic process. If you want to transfer, I don't know, 1 micron, due to the scattering of the radiation, instead of transferring 1 micron, you will transfer 3 microns. So bye-bye your portable mobile phone, and let's return back to the telephone cabin that was used to say with my girlfriend. Okay? You lose resolution, you lose the possibility to miniaturize the device. On the other side, if the striking radiation will strike on an optically flat surface, the reflected beam will be perpendicular. So you can faithfully transfer the correct dimension of your features. Okay? So without an optically flat surface, there is no way to improve the resolution and to properly apply and implement the lithographic transfer process. There is no way to reduce and scale down the dimension of devices. Okay? Is it clear? So, as a consequence, most of the silicon wafers that you may retrieve on the market are so-called SSP, single-side polished. Okay? This is, for instance, an example of a single-side polished, because it has just one side that is mirror-like, while the other is just lapped, but not polished. Okay? This is the standard. Okay? The standard type of wafer that you may retrieve on the market. Nonetheless, you may also find into the market DSP wafers, double-side polished. This is, for instance, as you can see, optically flat and optically flat on both sides. Okay? So this is an example of a double-side polished silicon wafer. Why making double-side polished silicon wafers? What do you think is the aim? Just let me explain. Double-side polished silicon wafers are typically 2 to 10 times more expensive than single-side. Okay? 2 to 10 times more expensive. So why commercializing, fabricating double-side polished silicon wafer if they are so expensive? What is your opinion? This is the correct answer, okay? The correct answer is that the double-side silicon wafer are required whenever you want to perform lithographic processes on both sides of the wafer. Okay? There are some devices that will involve lithographic processes to be performed both on top side of the wafer and on the back side. One example that will become very, very, very popular to you in the next month is this one. I don't know, this may be silicon oxide. And this could be for instance, piezo resistors. I hope that at home you will be able to see the blackboard, okay, but it seems so. What is that? This is a very, very simplified section of a micropressure sensor, of a differential micropressure sensor. That is a miniaturized device that is able to measure the difference of pressure. If you have a smartphone with the pressure capability, with the pressure sensing capability, a smartphone acquired in the last year, it has this functionality, it has this kind of MEMS device inside, okay? It works on a very simple principle. If you have a pressure P1 on the top side and a pressure P2 on the bottom side, the difference between these two pressures, the so-called differential pressure, will cause a deflection of this membrane. This membrane is usually of the order of a few microns. It may be both an upward or downward deflection, of course, depending on which among P1 and P2 is the largest pressure. Okay? Then, if you give a look to this device, or better, another important information is that the mechanical deformation of this membrane is sensed and transformed into an electrical signal by the piezoresistors. Piezoresistive materials are materials and devices that convert a mechanical stress into a variation of resistivity. From an electronic point of view, into a variation of resistance. Okay? So the deformation of the membrane is sensed by these piezoresistors. Piezoresistors that are placed on the membrane. When in Grenoble, and when dealing about pressure sensor and their related technologies, I will explain which is the correct location of these piezoresistors so as to optimize the output sensitivity. Okay, so they cannot be placed randomly on the field. They must be placed exactly in one position because that position will optimize the sensitivity. Okay, what is the result? The result is that if you want to define the shape of the top piezoresistor, what we typically in technology say, if you want to pattern the piezoresistor, you need to exploit on the top side a lithographic process. If you want to fabricate this suspended membrane from the back side, you need a lithographic process. Okay, so this is an example of a microsensor, of a micro device, in which you are required to perform lithographic processes, lithographic transfer, both on the top and on the back side. And if I can add a further details, the most critical issue for this kind of devices is to align in X, Y, and theta what you do on the top side with respect to what you do on the back side. The piezoresistor must be axial with respect to the membrane and not shifted laterally. Okay? So this is a typical situation in which, due to the double lithographic requirement, you need double side polished wafers. Okay? So this is a roughness at the end that is not good for the optical transfer. Okay? Okay, just let me have this slide, and we will have 10 minutes of break time. Okay? Sorry for today, just 10 minutes, but the process for the fabrication of wafers is nearly finished because at the end you just have the wafer cleaning. Okay, so the wafers are washed and rinsed in water, typically ultra pure deionized water, that in a 3 lecture I will explain you how to obtain. Okay, this is of course to remove all the abrasive slurry, all the abrasive or chemical etchant that have been exploited in the previous steps. And as a final, not mandatory processing step, sometimes the wafers are laser marked, okay? Laser marked, so has to introduce on a lateral location, okay, the production lot code, the date, some data about the thickness of the type of dopant for the resist, and so on, okay? So it's a sort of code, recognition code for the wafers. Is okay? Any question? Yes?
This pattern that's observed on the lithographic process, right, from another.
This one?
Yeah, like
You ask how this code is transferred onto silicon? Ah, okay. So for the students that are at home, the question is if this pattern is due, this square pattern is due to the lithographic process. The answer is yes. Moreover, it's not only a point that the pattern is a square for the lithographic process. The pattern is usually square or rectangular because at the end, the wafer must be separated into single chip. Okay, what is called the singulation. Okay, we will analyze this process in the lecture dedicated to the back-end technologies. So you need to, you need to separate the wafer into single dices. And of course, the square or rectangular ordered, arrayed placing of the chip will favor this separation. Okay. For what concerns the code, I just forgot to say that this is obtained through laser transfer. So it's a laser marking or engraving into the silicon surface. Exactly. Very, very quick and summary, but this is excellent. Okay? Anything else? Okay, perfect. So let's have 10 minutes, a little bit more than 10 minutes, and let's restart at 1:40. Okay, I will also write on the chat. Okay. Start the recording of the lecture. Okay, just to finish this lecture about the wafer preparation. Okay, we still have to comment a little bit about the diameter of the wafer. Okay, what you see reported in this slide is the history. The history of the evolution of the silicon wafers from the first 1 and 2 inches wafers to the current technology based on the 300 millimeters wafer. Okay. Just to be clear, here in this picture you see in particular what are the 2 current standards for both the microelectronic, so integrated circuits fabrication, and MEMS industry, MEMS devices. Okay, for MEMS devices, the typical standard is 8 inches wafers, that is 20 centimeters. For the microelectronic industry, integrated circuits fabrication, the current state of the art is 12 inches, that is 30 centimeters, the so-called pizza wafers. Just because you're in Italy, I think it's quite mandatory. Okay. The next frontier, okay, the next state of the art will soon be the 18 inches diameter that are 45 centimeters. Here you see This is just a prototype, a sample. As far as the last semester, I was used to say that these wafers were expected in production by 1820, okay? But it seems that if you give a look to the recent publications, and in particular recent means, recent means August 2020, okay? At least one company, I didn't have the time to search for all the other, but at least one company, this Pure Wafer, has started providing to the market with 450 millimeters wafers. But again, it's a very, very recent news, because up to the last semester, up to the student of the last semester, February, March, April, and May, these kind of wafers were just prototypes, research case, but not available on the market. Okay? I also gave a look to the database of this company. Okay? Now, I'm pretty sure that I'm making an error. Sorry, not this one. Ah, perché non mi fa condividere questo? Ok. Okay. So this is just to give you an idea, the database of the wafers that are commercialized by this company, okay? Just downloaded this morning, okay? So here you can see how many different type of wafers is possible to acquire from this company. And the same is whatever is the provider you're looking for, okay? But in particular, if you give a look to this column, okay, this column is the column related to the wafer diameter, okay? If I'm not wrong, I put them in order of diameter. You see how many 2 inches, 4 inches, 3 inches silicon wafers are available, and how many few 18 inches wafers are currently available, okay? So just 5, and to be correct, just 4 type of silicon wafers, because this one is Boroflot, so it's not silicon, it's glass. Okay, so this one is not to be considered, it's not silicon. Okay, the only silicon wafers are this one, and these other 2. Okay, so just 4 types of 450 millimeter silicon wafers currently commercialized. This is a very, very last update, okay? Yes, tell me.
Yeah, what is complicated to make complete?
Okay. So the question from your colleague is why it is so complex and so technically challenging to fabricate wider diameter wafers. The problem is, The problem is in the control of the most important parameters in the Czochralski process. If you want to obtain regular, mostly defect-free, homogeneous in terms of axial composition, silicon ingot with a Czochralski process, okay, it's very, very hard and complex and challenging. Sorry. Because the larger is the diameter, the stricter must be the control on the temperature, the pooling speed, the rotation speed, the atmosphere in the reactor, and so on. For instance, a very critical issue in the Czochralski process, I didn't provide all the detail, is the radial composition, the radial contamination, the radial quality of the monocrystalline building. Okay, so the wider is the ingot, the more technically challenging and technically complex is the Czochralski apparatus, and that's the most important limit. Then, in cascade with respect to the Czochralski process, all the other cropping, checking, slicing, lapping, polishing, they must be performed on a surface that is wider and wider, always preserving the same features that you got on the smaller surface. And that's always critical. Consider that, okay, today you see this slide, okay? I'm sorry. I'm sorry because your colleague are not able to see the correct slides. Another point that is relevant besides why it is so challenging. The next point is why it is so relevant. So what is the advantage in obtaining larger diameter wafers, okay? Well, I think it should be quite intuitive, okay, that if you start from a 2 inches silicon wafer and you double the diameter, okay, you will have an advantage, okay, an increase in terms of gross surface area available for the fabrication of devices that is geometrical, okay? So if you have a linear increase of the wafer diameter, you will register, just for trivial geometrical reason, a geometrical quadratic increase of the available surface for the fabrication of devices. Quadratic increase, that means quadratic increase of the number of devices that can be fabricated per single wafer, and if the dimensions of such devices do not change, and this is not typically the case of the microelectronic industry, but let's assume this is the case just for simplicity, you will scale down quadratically the manufacturing cost of the single chip. Okay, so that's extremely important. The second point that is highlighted here is that the first line is just an evaluation of the advantage related to the gross surface increase. But if you consider that when you perform a lithographic transfer, I will show you that there is a ring at the periphery of the wafer that is called exclusion zone or black ring, in which you cannot transfer anything. So in which you cannot fabricate devices, okay? This is, for instance, a picture of a real wafer. You see how many chips have been fabricated in the middle, but there is a ring at the periphery that is useless. Again, I'm sorry because probably it's too far to appreciate, but this is a wafer with a blue layer on top. Okay, the blue layer is silicon nitride. It's very thin. I think it's not fully appreciable, maybe in this way, but there is a ring here at the periphery that is 2 millimeters, in this case wide, in which there is no deposition at all. No deposition, no fabrication of devices, okay? The point is that this black ring, I will show you and I will explain what it is due, okay? In the lithographic lecture, I will explain why this ring exists, the ring is due to the so-called hedge beads, and I will explain what they are related to. Today, what is relevant is that this ring, the width of this ring, is independent with respect to the wafer diameter. Okay? So the width of this ring is always 1 millimeter, 2 millimeters, 3 millimeters. But for a certain technological process flow and technological apparatus is always the same, independently with respect to the wafer diameter. So if you have always the same ring width, okay, when you increase the wafer diameter and you calculate no more the gross surface area, but the net surface area, that is say the total one minus the ring surface, okay, the advantage is more than quadratic. Okay, so you see that the advantage is more than 4 per if you double the diameter, is more than 9 per if you make the diameter triple, is more than 16 per if the diameter is 4 times larger. Okay? So this is an important advantage. Second point, or if you prefer, under another point of view, what you see here in the bottom is the footprint, okay, of a typical chemical vapor deposition reactor. That is an apparatus, again, you will be familiar with, that is very common for the deposition of thin films, thin layers, okay? This is the footprint, or better, is the footprint of the wafer holder, okay? This is where you place your wafer before closing the reactor and performing the deposition. Now you can see, let me zoom because it's easier. Okay, this way. You can see here how in this CVD reactor, one wafer that is 6 inches wide, okay, 150 millimeters, is able to provide a much larger surface, the red one, with respect to 7 2-inch wafers. So if you place together 7 2-inch wafers, the blue one, inside one single 6-inch wafer, and for the 6-inch wafer, there is a larger surface available for the deposition. Practically, the difference is the red one. Okay? So even if the two kinds of wafer will occupy the same footprint, the strategic advantage of the larger one is to provide a larger surface. Larger surface available for the deposition, larger surface available to increase the number of devices you can manufacture. If you can increase the number of devices you can manufacture on a single wafer, you can maintain or keep the fabrication cost lower. Okay? So that's the strategy, and that's the fundamental reason why there is a huge and continuous effort in making wafers and substrate always larger. But consider, just to give you an idea, that passage from 12 inches to 18 inches required 7 to 8 years of technological development. 7 to 8 years. So it was a very, very long development story. Okay? It's not trivial. Okay? Okay. I think that this first lecture should be completed. Have you got any questions before quickly start moving to the next one? I need to start the next one today, okay? Any question in the room or at home before starting the next lecture? Okay. It seems not. Okay, so let's start briefly, at least the second lecture. This lecture will be dedicated to crystallography and crystalline defects. Preliminary information. Crystallography is a very complex subject, okay? This lecture, on the other side, will be very short. I mean, to provide a full lecture about crystallography and all the crystallographic details related to the semiconductive material, it would require some tens of hours that, of course, will be out of the scope of this course, okay? So the aim of this course, the aim of this lecture is to provide just a minimal survival kit, okay? To be able to move across the world of Miller indices, crystallographic orientation, crystallographic defects, and so on. Okay, so it will be very short, just a minimal survival kit. Okay. So, besides this premise, okay, you know that generally speaking, and in particular in this technological domain, we may have to deal with three different types of solids. Okay, they may be monocrystalline, polycrystalline, or amorphous. With the monocrystalline being characterized by the fact that all the atoms are arranged on a regular grid that is called lattice. The polycrystalline that are characterized by different grains, each of them singularly considered monocrystalline, but reciprocally, randomly oriented and separated by discontinuities that are called grain boundaries. And finally, the most disordered structures that are the amorphous material with absolutely no order, even at a short range and at a molecular scale. Okay? For what concerns the topics covered by this course, you will see that in the future we will deal with all these three types of materials. Okay, so in microelectronic industry and in MEMS fabrication, okay, we exploit both monocrystalline materials, typically the substrate, but also polycrystalline and amorphous. Nonetheless, today, we will cover and deal just with the monocrystalline materials. Okay, so the minimal survival kit is dedicated and focused on monocrystalline materials. Monocrystalline structure, we have said that the atoms are arranged on a regular structure, on a regular building, on a regular grid that is called lattice. There are just 14 unique possible lattices in the three dimensions that are called Bravais lattices. Okay? You see that they are cubic, hexagonal, tetragonal, orthorhombic, monoclinic, and triclinic. Moreover, with most of them, not all of them, but most of them, that can be subdivided in further different subtypes, okay? The most important kind of lattice we will deal with in this course, since covering mostly the silicon technology, will be the cubic structure, okay? Well, not all the semiconductive material will have a cubic structure, okay? Moreover, there are some semiconductive material that may have more than one crystalline structure. Okay, for instance, just to cite a relatively popular case, silicon carbide is one of these materials. Okay, silicon carbide is a semiconductive material used for high temperature, high power electronics or harsh environment microsensor. Okay, silicon carbide is one case of a semiconductive material that may be exploited in the industry both as cubic, in particular it is called 3C silicon carbide. The number 3 is just a number that represents the layer, the periodicity layer in the structure of silicon carbide. The C stands for cubic. But the silicon carbide that is used in technology, it may also appear with two different forms. And the two different forms are 4H silicon carbide or 6H silicon carbide. And since they are H, the H stands for hexagonal. Okay? So silicon carbide is one case of a semiconductor material that instead of being characterized by a single, unique monocrystalline structure, may crystallize under different forms. Okay? In particular, it may crystallize in 96, if I'm not wrong, 96 different forms. Okay? Because being biatomic, the situation is a little bit more complex and there are more combinations. But among these 96 different configurations, just 3 are relevant for human and technological applications. 1 is cubic, 2 are hexagonal. Okay? Nonetheless, as already said, we are mostly dealing with the silicon technology. And as I will show you, silicon belongs to the cubic family. Okay, so in the following, we'll focus mostly on the cubic structure, on the cubic lattice, and on the cubic crystallographic orientation. Cubic crystal structure. Okay, as anticipated by the previous table, the cubic crystal structure may appear in nature under 3 different forms: simple cubic, body-centered, and face-centered cubic. Okay? In the simple cubic, we have 1 atom at each edge of the cubic cell. In the body-centered, we have 1 atom at each edge plus 1 atom at the center of the cube. In the face-centered cubic, we have 1 atom at each edge plus 1 atom at the center of each of the 6 faces of the cube. Okay? The first one, even if extremely simple, is also the most rare, since basically only polonium may crystallize under this form. The second is typical of alkaline ions like sodium or some metals, chromium, iron, and so on. The last one is also typical of noble metals like gold, platinum, but also aluminum and copper. So different elements may be characterized by the same cubic structure, but of different subtypes. Okay? Cubic, body-centered, face-centered. Moreover, even if 2 different elements may share the same subtype of cubic crystal structure, they are characterized by the different lattice parameter, where the lattice parameter is nothing more than the length of the cube side. Okay? So 2 different elements, even if sharing the same crystalline structure, they usually have 2 different lattice parameters, 2 different lengths of the cubic structure in the cubic cell. Okay? What about the case of silicon? We have said that silicon belongs to the cubic family. And in particular, the structure of silicon, but also the structure of germanium is absolutely the same, is known as diamond structure, okay, and belongs to the family of cubic crystals. It consists, pay attention, it's not so easy, I'm not a magician, but it consists into a couple of face-centered cubic structures that are interpenetrated each other along the diagonal of the cube, and this interpenetration stopped at 1/4 of the diagonal of the cube. If you prefer, instead of the forward movement, you can use the backward one. You consider 2 face-centered cubic structure superimposed, and you shift them along the diagonal of the cube of 1/4. The result will be the same. The result is what is depicted here in this drawing or in this animated GIF that allows you to have a look around the different angles to the same silicon structure. The effect is that each silicon atom is surrounded by 4 identical silicon atoms that are placed at the same equal distance with the same identical angle, okay, at the corner of a tetrahedral structure. Okay? So this is the monocrystalline structure, the monocrystalline building that characterizes monocrystalline sorry, this is the crystallographic structure that characterizes monocrystalline silicon, and it is unique. Okay? Just for curiosity, 3,5 compounds like gallium arsenide and indium phosphide share the same crystallographic structure. Okay? The name is different. Instead of speaking about diamond structure, we speak about zinc covalent structure, but it's exactly this one. The difference with respect to the silicon case is that in the silicon, all the atoms are equal. In the gallium arsenide on indium phosphide, the two atoms will be different. Okay, so for instance, each gallium atoms will be surrounded by four arsenic atoms, and vice versa. Each indium atoms will be surrounded by 4 phosphorus atoms, and vice versa. Okay? But the structure is exactly the same. The lattice, the grid is exactly the same. Of course, the length and the distance between atoms will be different. Okay? This is another important difference. Is okay so far? Okay. So, this is the bulky structure of silicon. I mean, okay, this is not silicon. But if this would be silicon, this is the bulky structure of silicon. Okay? Nonetheless, in technology, in particular when we deal with thin films, and wafers are not exactly thin films, but wafers are bidimensional material, okay, because they are mostly surfaces that are relatively thin. We are not only interested in what is the crystallographic structure of the material, but is also relevant to determine along which directions the material was cut. Because cutting the material along different directions, cutting the materials with different cutting planes, will provide the same crystallographic structure, but different surface properties, because you will obtain different surface atoms arrangement. The same silicon cut along different directions will generate, in terms of properties, in terms of surfaces, completely different physical, chemical, optical properties. Be careful. When I say completely different, I will show you some cases in the future. I do not mean few %. I mean orders of magnitude different. Okay? Orders of magnitude. I will show you, for instance, in terms of chemical properties, that some crystallographic orientation, because the material, the bulk material is always the same, some crystallographic orientation are 1,000 of time more inert to the same chemical agent than other surface orientation. It's the same material, just cut along different planes, 100, 1,000 of time more resistant. Okay? So, well, due to this premise, due to this introduction, it is not only important to be aware and to be able to describe the bulky monocrystalline structure of silicon, but it's also important to provide information, so to describe the surfaces, to label, to identify the surfaces. With the aim to identify these surfaces, okay, we can use the so-called Miller indices, okay, that are basically 3 digits. 3 digits that uniquely identify specific surfaces, or if you prefer, specific crystallographic cutting planes with respect to the same monocrystalline bulky structure. Here I reported one example of calculation. So I reported the procedure, the simplified procedure for the calculation of the Miller indices. Okay. Then in the next slide, we will have an example. So let's suppose that we are dealing, just for simplicity, with a simple cubic structure, as you can see in this drawing. And in this simple cubic structure, we want to retrieve, to calculate the Miller indices of the red surface. Red surface that is parallel to the YZ plane or perpendicular to the x-axis, if you prefer. The procedure consists in, first of all, determine the x, y, and z axis intercept. For this red surface, the intercept are 1, infinite, and infinite. Obvious, okay? The second point consists, the second point consists in taking the reciprocals. The reciprocal of 1 is 1. The reciprocal of infinite is 0. The reciprocal of infinite is 0. And the third step consists in reducing the 3 digits to the smallest common integer. 1, 0, and 0. The smallest common integer is 1, 0, and 0. Okay, there is no change. So 1, 0, 0 are the 3 digits, the 3 Miller indices that identify this plane. Okay? This example is simple, but not significant. So I added this one. Okay? I'm used to have this example on the blackboard. Instead of drawing on the blackboard, I will use this tool, but it's absolutely the same. So let's try to calculate the Miller indices of this surface. This surface, this Canty surface, whose intercept with the x, y, and z axis are 2, minus 3, 4. First step. The second step in the procedure, in the protocol, if you remember, consists in taking the reciprocal. The reciprocal are, of course, 1/2, minus 1/3, and 1/4. The last step is to consist in reducing everything to the smallest common integer. Between 2, 3, and 4, the smallest common integer is 12. Okay? That is to say, 6 12s minus 4 12s, 3 12s. You eliminate the 12 from all the denominators, and what you get is the triple digit 6 minus 4, 3, that are exactly the Miller indices depicting this plane, labeling, identifying that plane. Okay, so it's a quite easy procedure. It's just mnemonical, but absolutely simple. Okay, moreover, usually the minus in the digit in the Miller indices, the minus sign before the digit is never used, okay? Don't ask me why, because I don't know. But instead of the minus in front of the digit, you use an horizontal bar over the digit. Okay, so this horizontal bar over the digit is the labeling for the minus sign. It's okay. It's okay so far. Okay. Well, okay, just a couple of slides, then we will close. What about, again, the silicon case? For the silicon technology, the 3 most important crystallographic orientation are the 100, the 110, and the 111. That is to say, for the 100 is the crystallographic orientation parallel to the crystallographic axis. Sorry, perpendicular to the crystallographic axis, parallel to the crystallographic planes. Okay? Parallel to the faces of the cubic cell. For the 110, we are dealing with the orientation that are parallel to the diagonal of the faces of the cube. The diagonal of the faces of the cube. Okay, parallel or perpendicular, of course, is the same for geometrical construction. For the 111, we are dealing with the surfaces that are perpendicular to the diagonal of the cube. In this case, is the diagonal of the cube from one edge to the opposite one. Okay? So these are, without any doubt, the three most common crystallographic orientation. The dominating, from a market point of view, crystallographic orientation for silicon wafers and monocrystalline silicon layers, thin films. Why just this one? And what are the differences between them? I mean, why you should acquire a 100 or a 110 or a 111 silicon wafer? For instance, let's analyze the semiconductor industry, so the microelectronic industry. For the microelectronic industry, the 100 orientation, as I will show you, is the one with the lowest concentration of dangling bonds. So it's the one with the lowest concentration of surface defect. So is the most suitable one for the fabrication of MOS field effect transistor, metal oxide semiconductor field effect transistor. Because in this kind of devices, the metal and the semiconductor material are separated by a thin oxide layer. Thin oxide layer that in the current technology is of the order of a few nanometers. Okay? So the thickness of this oxide layer is so thin that if the surface of the semiconductor material is the best one from the point of view of contamination, so minimal concentration of dangling bonds, it will result, as a consequence, also in the optimal quality of the extreme thin oxide layer that separate the metal and the semiconductor material. Okay? So for the CMOS, for the MOS technology in general, 100 is the best solution, generally, because of the lowest concentration of dangling bonds and so crystallographic defects. For the case of the BJT technology, bipolar junction transistor technology, okay, the best preferred one is the 111. Why the 111? Because, as I will show you in one of the very next lecture, the 111 is the crystallographic orientation with the largest surface atoms density. So it is the configuration in which you have the largest concentration of silicon atoms exposed at the surface. Being exposed at the surface, they are more prone, more available, more ready, for instance, to react with oxygen so as to provide oxidation. The 111 crystallographic orientation is the one with the fastest oxidation rate. And I will show you that the difference between the 111 and the 100 is not 2%, 3%, is 70%. 70. Okay, 70% difference. Even if the crystallographic structure is the same. Only the orientation change and the availability of atoms at the surface ready to be oxidized. So this is a couple of comments for the microelectronic industry. In MEMS and in microsensor technology, for instance, in one of the future lectures, we will speak about etching processes, wet etching processes. Okay, I will show you that the same wet etchant, okay, the simplest wet etchant for the silicon technology is potassium hydroxide. Okay, it is so big, I think that also your colleague at home will be able to see it. Okay, potassium hydroxide is the most typical wet etchant for silicon, wet anisotropic etchant for silicon. Now, if you give a look to this drawing, you see that the same etchant, that is to say potassium hydroxide, for instance, if you change the surface orientation, so if you change from 100 to 110 will produce two different hatched profiles. In 100 oriented surface, the hatched trench will be a reversed truncated pyramid with a 54.74 degree angle, and you cannot change. The angle is fixed and is due to the crystallographic orientation. If the same etchant is used to hatch a 110 oriented surface, there is no way the hatched trench will be 90 degrees, and you cannot change it. Okay, so you see that the same material, monocrystalline silicon, with the same structure, subjected to the same etchant, with the same concentration and same temperature, will produce two completely different effects. In one case, the hatched profile will be a trapezoidal one and a reversed pyramidal one. In the second case, it will be perfectly perpendicular, simply due to the different crystallographic orientation. Okay? I think that is largely sufficient for today, okay? Of course, if you have questions, I will end this lecture by trying to answer them. Both for you and both at home. I know that you have another lecture in 1 hour and a half, if I'm not wrong. Yeah. The question from your colleague is, what are the dangling bonds and what is the effect of dangling bonds, okay? In an MOS device, okay, you have source, drain, oxide, and metallic contact, okay? This drawing, from a geometrical point of view, is of course wrong, because this oxide is actually this oxide, very, very thin, okay? So, if the surface of silicon is extremely defective, the dangling bonds are the unsaturated bond, because the monocrystalline structure of silicon at a certain point, so at the surface, is finished. So the last atoms, okay, have incomplete bonding. The lowest is the concentration of surface atoms. The lowest will be the number of dangling bonds. The dangling bonds are points in which elements are strongly reactive. So they strongly attract defects. Okay? The lowest is the concentration of silicon atoms. The lowest will be the concentration of dangling bonds. The lowest will be the concentration of contaminants. The best will be the quality of the nanometric oxide layer. Fundamental in MOS technology. Okay? Okay, the same question was from Yong Soon that asked to remind what are dangling bonds and okay. Okay, thank you very much for your attention. See you next Monday and enjoy your weekend.